My name is David Sherret, and I'd like to thank Derek and the team over at JsPoland for having me here today. I wish I could be over there in Poland, but you know how things are these days. A bit about me: I'm a software developer from Toronto, Canada. I've been programming for over 15 years now, and professionally for the past 8, working on healthcare and medical device-related software. The past 4 years of that I've spent working on software for neurosurgery, so surgical planning, navigation software used during the surgery, along with working on a robotic surgical microscope. Recently, there was some turbulence because of COVID, so I ended up being on furlough for a bit, then came back to my job on contract, and now I've quit to start a business with a friend. It's in the vehicle collision industry. And then there's my open source and hobby work. This is where I spend a lot of my time using JavaScript, but actually mostly TypeScript. I've created a few static analysis and code generation tools, most notably tsmorph, which is great for large-scale programmatic refactors and analyzing TypeScript and JavaScript code. Recently, over the past year, I've started working on a code formatting platform called dprint. It's written in Rust, so it's super fast. At the moment, the TypeScript and JavaScript code formatting plugin is being used in Dino as the Dino format command. Works pretty well right now, but still have a lot of work to do, but I'm pretty happy with it overall after just 1 year. Finally, you can find me on Stack Overflow answering questions on the TypeScript compiler API tag. Okay, let's move on to the talk. So this is a talk on JavaScript code generation tips. We'll look at what is code generation, why would we want to code generate, an example of code generation, and finally, tips for generating JavaScript code. This should go without saying, but everything I say here is just my opinion and what I found works for me. You should always understand the reasons why you should do something before you apply it. There's always edge cases and exceptions. Basically, find what works for you, and I hope it aligns with what I'm going to show you here today. So first, what is code generation? Well, we use forms of code generation all the time when compiling code, using Babel, going from some future version of JavaScript down to an old one. Using TypeScript, it's a similar deal to Babel. But that's not what we're going to look at here today. Here we're going to look at a subset of code generation, which is generating code based on data. So we could have a non-JS code data source, such as a database, file on the file system, or some non-JS language. Or we could also have a JS data source, which is basically statically analyzing the JS code, then generating code from it. So why code generate? It's an important question we have to answer. What's the benefit? First of all, it can create a single source of truth and help us align with the don't repeat yourself principle. This means that if we make a change to something, we only need to change it in one place, that is, at the source of truth. This is a benefit because if we have multiple sources of truth maintained manually, they might accidentally get out of sync with each other. We might update one place, but accidentally forget about the other, which might introduce a bug in our code. Generally, you'd want to restructure your applications to not use code generation in order to solve this problem. But sometimes it's not the best solution, as the data might be in another language's code or in a place outside our JavaScript application that's not accessible at runtime. This is where code generation can sometimes come in. Without code generation, we'd find ourselves manually maintaining these multiple places, but with code generation, we can change it in one place, rewrite our code generation script, and it's automatically updated. The code is automatically updated to reflect the change at the single source of truth. I want to emphasize this point, but what code generation allows you to do is to have a single source of truth and then derive functionality from that source that would otherwise have meant an additional source of truth embedded within that functionality. Second point is automatic maintenance. A lot of times we might find ourselves mindlessly maintaining or writing code from another source. This is a waste of time and an error-prone task. It would be better to eliminate this completely. Code generation can help by automatically maintaining this code to help us lower the chance of making a mistake. Obviously, writing a code generation script has an upfront cost, but it might save you time in the long run. One big benefit is that with code generation, you can remove unit tests from your maintenance burden. I guess if you really wanted to, you could code generate unit tests too, but I think that's probably a waste of time. Just reviewing the code that's code generated is probably good enough. I do believe, though, that you should still run integration tests that use that generated code. That way you can make sure everything is working well together. Third point is synchronized type information. Sometimes if you analyze a source of data, you can figure out type information from it and then add that type information into the generated code. This can be done by putting information in JS docs. Talking about how to write these type annotations is a subject beyond the scope of this talk, but if you're not familiar with it, you should search online into using JS docs to store the type information. For example, here is a simple function call that describes what the first object parameter looks like. Then when we call this function, our editor, such as VS Code, will show us what this function expects. If you're using TypeScript, this is obviously a must-have and very beneficial. Having the type information allows us to close these statically typed gaps where previously we wouldn't get compile errors. Fourth point is performance. Code generation can sometimes help you do checks or optimize functionality before runtime that otherwise would have had a runtime performance cost. That said, it's probably an extremely rare scenario to encounter where this would make much of a difference, but there are those scenarios. Finally, let me just say it's not always worth it. Code generation may introduce a lot of complexity. It may have too small of a benefit in some scenarios. And sometimes an analysis-only solution may be good enough. For example, you could do the analysis portion, store the result in a JSON file. Then when your application loads, you could load that file and dynamically generate the functionality from it. Okay, moving on to the next section, I'm going to show you an example of code generation. In this example, we have some JS code where our application exists, and we want to make a function call into another language's code. Here's an example of what that other language's code might look like. For the purposes of this example, it doesn't matter what this language is. Just know that this is a function called createNote that takes three parameters: title, which is a string with a max length of 255 characters, text, which is also a string with no max length, and is pinned, which is a Boolean. Ideally, when we'd call this function in our application code, we'd want it to be as simple as possible. I think this shows that. We'd create a createNote function call, and we provided an object with title, text, and isPinned properties, which correspond to the parameters in our other language's function. Then behind the scenes, that function call would go and make the call into other languages' code. The problem, though, is we'd need to write this low-level glue code. Here's the declaration of createNote, and in it, we're first verifying the input of the function. So checking that the title on params is a string, that it's under or at 255 characters long, then that the text property on params is a string, and finally that isPinned is a Boolean. Note that we're also providing the property names to these assertion functions so that we can get better error messages. Finally, the execute call function occurs, and in it we provide the name of the function we want to call, which is createNote, and then we describe all the details about the values we're passing in, which includes the parameter name, the parameter data type, and finally the value. In this example, the assertion functions, as well as the execute call, parameter, and data type, are manually maintained. So as you can see, writing these functions, it's very tedious and error-prone. What's worse is if we change the code in our other language, for example, change the title to have a max length of 100, as shown here, we might accidentally forget to update our JS code to reflect that. Now we have a bug. This code no longer throws in scenarios it should, and that's not what we want according to our requirements. In this case, it would be best for the functionality to always be derived from the source of truth in the other language's code and automatically maintained in our JS code. This code being code-generated completely eliminates bugs like this from happening in our code base. Okay, we've looked at what code generation is, why we would code generate, an example of code generation, and now finally we're going to look at our main topic, which is tips for generating JavaScript code. Everything I'm going to show you here is mostly things I've done wrong, but also things I've seen people do out in the wild. Well, as you know, a big part of code generation is outputting the code as a string. But how would you go about creating that string? That brings me to my first tip, which is to avoid generating code using JS compiler APIs. The Babel and TypeScript compilers have functionality called node factory functions, and these are used by the compiler to generate code. So if they're used by the compiler for code generation, some people might believe it would be good for them to use it for their code generation purposes as well. I think that's a mistake. The compilers are made for and optimized for compiling. And just because something is good for compiling doesn't mean it will be good for other purposes. I say not to use these APIs because they're overly complex for our scenario. Instead, we can simply concatenate to a string. That said, using these APIs can be great for just analyzing JavaScript and TypeScript code. To solidify my point, this example shows using the TypeScript compiler's node factory functions to output the string shown on the right. An example using Babel would be very similar to this. I'm not going to even bother explaining this, but just note it's very complicated. Compare that to just using a string builder. In this example, I'm creating a writer object, writing a line with the specified text, and then finally outputting that to a string. This is much easier to understand. It will also be faster, use less memory than if we use the compiler APIs for this. Just a side note, this example uses my CodeBlock writer library. It's a library that you can use to help you output JavaScript or TypeScript code. It's basically a string builder with a bit more functionality. Second tip, avoid dealing with indentation in line. By this, I mean you should try to minimize the complexity of your code generation code so it doesn't have to worry too much about indentation. Take this code here. Again, the code on the left is the code generation code, and the code on the right is the output. Look at the second line that appends to the string. The indentation is hard-coded here, and overall, it doesn't seem too bad, but imagine if this was indented down many levels. The code generation code is already complicated enough, and we don't want it to bother dealing with tasks like this. We should use a solution that handles this for us. This is better. We have a writer object that is constructed by specifying the number of spaces to use for an indent. Then the rest of the code is written without dealing with those specifics. So if we wanted to change the output to use tabs, we could do that by modifying the constructor call of this writer as now shown. Technically, we're still dealing with indentation here, but it's at a higher level and it's easier to manage. Here's an example showing a function that can be called that will format the outputted code correctly at any indentation level. Again, the indentation is handled for us by the writer. Alternatively, it's always possible to not deal with indentation or formatting at all. You can simply run the final output through a code formatter like Prettier, or use the one I wrote if you like it. Next tip is to simplify what we're analyzing, then use that simplification in the code generation code. Basically, the details available when doing the analysis might be very complicated, or it might be a bunch of different steps for getting that data. To help reduce the complexity of the code generation code, we should reduce the details to only what we need. For example, when analyzing this function from the other language, the process of getting the details about it are a multi-step complex process. We should have an analysis step that executes these complex steps and produces a simplified view of the data we want, as shown here in this object. Next tip goes hand in hand with the last. Analyze, then code generate. This is very important. You need a clean separation between your analysis and code generation and make this a two-step process. If you mix the two, then your code will become super complex very quickly. For example, in this code here, it's calling a function that will go out and analyze all the functions in our other languages code. It will create those simplified objects we talked about in the last tip and return them. Then our code generation code can use these simplified objects to output the generated code. A huge benefit of making this a two-step process is that we've now decoupled our analysis from our code generation, so we can use that analysis for other purposes unrelated to our code generation. Next, hide caching and lazy analysis. Sometimes it might be very expensive to compute something you're analyzing, and for performance reasons, you want to cache or defer it from being computed. This makes a lot of sense, but if you do it, you should hide the details of this caching and lazy analysis from the code generation code. It should be something that's hidden behind the scenes in your analysis API. Code generation code, it's already complex enough, and you don't want to make it more complicated by exposing those details to the code generation code or making it handle it. Next tip is to avoid failing silently when analyzing. This is pretty important. If the data presents a scenario you haven't handled, prefer throwing an error as opposed to failing silently. The reason is because it might be an indication of something you need to handle, and not handling it might be a bug. So as you go along, you can figure out if you need to handle something. If something throws, you can then update the code generation code to handle it if you need to, or you can get it to explicitly fail silently or just be ignored. This also helps you to incrementally implement code generation. This is my favorite tip for all of you here at this JavaScript conference, and that is if you have the ability to analyze for type information, then you should generate code with that type information. In this example, the function in the other language has type information about the parameters, and based on that, we can generate a function call that has this type information in the JS docs. For example, we know that title and text are strings, and isPinned is a Boolean. We also know all their parameter names, so we can annotate the params parameter to be typed as an object with properties that go by these names with their corresponding type. This is huge because now we get code completion in our editor, and when we call this function, at least in VS Code, we'll get the type information. Up next is put the generated code in source control. I've had some disagreements with people over this one, but I would recommend treating the generated code just like the rest of your code. In my opinion, it's better to be able to review this code in pull requests and pull reviews as another form of validation on the generated code. It also might help you catch bugs in the generated code, and it helps everyone easily see how changes made to the code generation impact the output. A sub-tip within this tip is that if you're doing this, you should obviously ensure the output is deterministic each time you run it. You don't want the order of generated function declarations to change on each run or drastically change after making a small change elsewhere. Next is to clearly define what you've code generated. This is something I haven't been good at. If you've gone into any of my repos, I'm very sorry. So first of all, if you're generating an entire file, you might consider giving it a generated suffix as shown here. You may also want to add comments that state the code is generated, as well as explaining how to run the code generation. The reason I recommend using a file naming convention is one problem with only having a comment at the top of the file is that people may dive into the middle of the file and not read the comment at the top and then start manually editing it, whereas they'd most likely notice in a file named a certain way. A comment stating code is generated is also very useful for situations where you're doing inline code generation. By this, I mean scenarios where you're generating code in a file inline with code that's manually maintained. So if you find yourself doing that, just be sure to clearly define with comments what's generated. Okay, my final tip of this talk. and it's to use tsmorph for inline code generation and programmatic refactors. Again, by inline code generation, I'm talking about scenarios where a file has both generated and manually maintained code. And by programmatic refactors, I mean scenarios where you make changes to a code base programmatically instead of manually doing it yourself. In these scenarios, I'd recommend to avoid using solutions that transform ASTs. I'm not going to get into what an AST is for this talk, but for people who know, I'd recommend not doing these changes by transforming ASTs because ASTs are lossy and don't have information like comments or whitespace stored in them. Again, compiler APIs are designed for compiling and aren't optimized for scenarios of changing code that humans maintain. They'll often trample over comments or change whitespace that you don't want to be changed. If you really must, use a compiler's text changes API. But overall, I would recommend using tsmorph, which is a library I created specifically for this scenario. It will be easier to modify TypeScript in JavaScript code. The code you write might not be as performant, but it will be way easier to maintain, and you'll save a lot in your development costs. Okay, that's the end of my talk. I hope you learned something. You can view my slides at the URL shown here, and thanks for listening.